Okay, so we're going to talk about segments and we're going to talk about angles, and those are sections 1.5 and 1.6 in our book. And our discussion starts with a postulate, which is called the ruler postulate. And again, a postulate is something that's an accepted fact. We can't prove it, but it gives us a starting point to deal with things. And so this one is a little bit wordy. We'll talk about it a little bit as we go through it here. But it says that the points of a line can be put in a one-to-one correspondence with the real numbers so that the distance between any 2 points is the absolute value of the distance of the corresponding numbers. So what that means is I could pick up a line and I could put it on the number line. So we have a number line down here. And let's say I started one point at 0 and I had the other point go to 4. If I was subtracting those two values and taking the absolute value of that, I would get the distance of that line segment. So you imagine picking it up, putting it there, and that makes sense in terms of how we think about distance before. And if we have two segments that have that same length, we say those are congruent segments. And there's our congruent symbol right here, the equal sign with the little tilde on the top. And so congruent segments mean that they have the same measurement or they're physically the same shape. So we can pick one up and put it on top of the other and they would match up exactly. So if we look at the example above, which of the two segments are congruent, which means the same? If we were to just look at the lengths of those, so I have 2.52 and 2.5, it should be pretty apparent that if I take up XY, I pick it up and I move it over here, it is going to fit exactly on ZW. So we say that those are congruent segments. They have the same measure, they're the same length, they have the same physical space that they take up if we were to put them on the number line in the corresponding positions. Something that we will use when we start getting into our proofs is the segment addition postulate. All right, so we have if 3 points A, B, and C are collinear, and B is between A and C, then AB plus BC equals AC. That might sound hard, but all it means is if you take AB and you add BC, you get the whole thing AC. So that makes perfect sense, right? If this is 2 and this is 3, the whole length is 5. More often than not, it's going to look like this where we have some expressions, but we can do the same thing to sort it out. So we're given MP is 25, and we can set up an equation to solve for x. So we set up an algebraic equation, we solve for x, and we get x is 15.5. And then we can use that to figure out what we're asked to figure out, which is MJ and PJ. So PJ is x plus 7, so I just add 7 to 15.5, and I get 22.5. And then MJ, I add up my two pieces using the segment addition postulate, and I get 38. So that should make some intuitive sense as we go through it. We also have something called the midpoint. And the midpoint should sound familiar. It's a segment. It's the point on a segment that divides it into two congruent segments. So they have the same measure. A midpoint, any line, ray, or other segment through the midpoint is said to bisect the segment. So we have kind of two root words here. Bi means two. Sect is part of like a section or a sector, which means we're going to cut it. So we've cut something into two equal congruent pieces. All right, equal meaning same measure, congruent means same exact shape. So if down here, if I'm given that M is the midpoint of my whole line segment, that means that the distance from R to M and from M to P are going to be the same. So we can set up an equation using our expressions and solve for x. So if we solve for x, I get x is 15, and then we can use that to answer the questions. So the questions ask for Rm and Mt. If we plug in our values of x, we get our values for 84 for Rm, and we should, because it's the midpoint, we should get that Mt is also 84. If we plug through it, we get 84 again. So that's a nice check that our math is correct because we got the same distance on both of these. All right, and then the whole thing, if we were to take twice 84, we get 168, which is the length of our whole line segment. All right, so we do a similar kind of progression, but now with angles as opposed to line segments. So an angle is formed by two rays that have the same endpoint, and that same endpoint is called the vertex. So if you recall, a ray has a starting point and goes in one direction. So I have ray BA and I have ray BC. Those go in that direction. This is the angle that's formed. So if I was to travel up from there to there, that angle is what we're talking about. There's three ways that I can name that. I can name it angle B because it's not ambiguous. There's only one vertex that B could be, so that's fine to just call it angle B. I could also name it ABC or CBA, where the vertex is in the middle as I name it. So I get three ways to name that angle. They all mean the same thing. You're going to see them all different ways. And if we want to actually measure that angle, we have a tool called a protractor. So we'll do a demonstration in class, but a protractor, is, you've seen them before and used them before, is usually a semicircle with the letters 0 to 180 degrees on them. Then you match up the vertex to the ray and get your angle measurement. It's very similar on that idea is our protractor postulate, which sounds harder than it is. But basically, if we're given a ray AB and the number 0 to 180 degrees, there's one ray with endpoint A extending on each side of AB, such that the measure of angle R could be formed. So we'll talk about how we measure things with a protractor. Our protractor postulate, again, just basically says we can create one unique angle as we go through this. What we will do a lot more is classify angles and use terminology as we go through this. So this is going to be kind of critical notation and terminology when we're talking about angles. So a lot of this is going to be familiar. But if I have an angle that is between 0 and 90 degrees, we call that an acute angle. If it's equal to 90 degrees, we call that a right angle. And if it's greater than 90, less than 180 degrees, that becomes an obtuse angle. That's how we declare it. And if it equals 180 degrees, this one we don't use it as much. It's called a straight angle. So also, we talk about a line, but if we want a terminology of angles, it would be a straight angle. Now we can see, if we think about it, right? Well, you say, well, what about that angle there as I go from here and I go bigger than 180 degrees? Well, the reason that we don't have to have another piece of terminology, it is true that we could go greater than 180 degrees, but we could always form an angle down here that's less than 180 degrees. And in geometry, it doesn't matter so much necessarily how things are oriented. So the angle that pulls through here, this angle, we could flip it around and get an angle that's similar to that angle up there. And so we can still call it an obtuse angle. Okay? Angles that have the same measure are called congruent angles. And there are really three ways that you're going to see this marked. The first is with the arc. So sometimes it'll be two arcs on the same angles would mean that they're congruent. You'll also sometimes see, as we go through it, a tick mark on the angles. So one tick mark would mean that the angles are congruent. If we want to actually use our, if we want to write it out, we have two things that we can say. We can say the measure of angle 1 is equal to the measure of angle 2, and equal to because they're a quantity, not a physical piece. Or we can say angle 1 is congruent to angle 2, which means the physical angle 2 can be picked up and put on top of angle 1. So if we're talking about equals, we want to use measure of. If we're talking about congruent, then we don't have the measure. We're talking about the actual angle as we go across. Right. So something to keep in mind as we look through this this unit. All right. Similar to our segment addition postulate, we have an angle addition postulate, which basically means if you take the two interior angles, so we have a measure of AOB, and then we have BOC, we can all guess that I'm going to get that whole angle there, and I would name it AOC. So that would be my angle there if I look at those pieces. Now this is a case where just calling it angle O is ambiguous. I don't know if we mean the green angle, the blue angle, or the entire one. So this is where I need 3 points to name the angle without ambiguity. If I am given a straight angle, so this is a this is a special case where I have a straight angle at 180 degrees. It's the same idea. AOB and measure of angle BOC is equal to 180 degrees because that's what a straight angle is. So it's just a simple substitution that allows us to get there. So we can use things like this to solve problems. So we have an example below. Now again, what we got to do is look at the information. This might look like a right angle, but we've been given that it's 88 degrees. So we want to figure out the rest given that. So I'm going to use my angle addition postulate. I know the whole thing is 88. I know that piece, angle 1 is 42 degrees. And then if I was to write it out, the measure of angle ABD plus the measure of angle DBC is the whole thing. So there's my angle addition postulate, and I substitute in the values that I know, 42, 88, I subtract, and I get 46 for the measure of angle 2. So that's probably overkill. You could probably figure that out without it, but that's the mechanics behind it if you're asked to show why it's working.